pointers. Yeah, we'd be starting to see pointers. That's right. We might even have finished, at the end of this course, we might have seen a binary tree. So, you know, slow down. Woo. So in a sense, things in life, there's all these exciting things to do. You've only got a finite amount of time to do as many as you can. So it's a race. You've got to A, pick the right things to do, so be clever, and then B, run as fast as you can. It's like those game shows where they used to have when I was growing up. Someone would give you like a shopping trolley, and you could run through an electronics store filling the trolley up. And you could have as much as you could put in your trolley in 60 seconds. And I think life is a bit like that. So you're rushing through the shop and you're grabbing stuff around. You could stop and say, oh, I say, bran. I'll have some bran. Or you could just go for the important stuff. So run fast, grab the important stuff, fill the trolley up. It's very consumer, isn't it? It's the idea is you're not in a supermarket, you're in the matrix. And you're in that library where you can download anything you want and learn anything at all. But you're only in there for 60 seconds because that's Neo's attention span. In 60 seconds, what can you learn? Sure, you could learn kickboxing and all those things like that, but why not download philosophy and quantum mechanics and poetry and awesome guitar playing and all that sort of stuff and learn the really cool stuff?
Or the username and passwords to log in later.
Yeah, or the username and password to log in later. Okay, now let's go. Oh, yes, okay, so we've got... these are my lecture notes. It'll be a bit cryptic for you guys. So I want to start by talking about Martin Gardner, because Martin Gardner died last week. I don't know if anyone knows of Martin Gardner or has read any of his work. He's a brilliant mathematician. He wrote the Mathematical Recreation column in the Scientific American for I don't even know how many years. He's published something like 70 books. And when I was growing up, it was really Martin Gardner that got me excited about maths. His books always made me remember what maths was really like. They were just full of puzzles and riddles and stuff and curiosities. He had a mind like anything. He was a polymath. And he would just write his little column, and in the column he'd talk about 7 or 8 things. And he wouldn't quite give the answers, and he'd hint at stuff, and he'd make you go away and do so much work. And this, as you can see, this is my sort of strategy with teaching. That his books would fill me with enthusiasm and give me pointers in the direction I needed to go. Then I'd run off and learn all that stuff. And over the years, whenever I go into a second-hand bookshop, there's a couple of authors I always look for. And I always go to the G section and look for Gardner. And if there's a Martin Gardner book there, I buy it without thinking, without question, no matter how much it costs, unless I've already got it. And even if I've already got it, I usually buy it because I can never quite remember which ones I've got and which ones I don't have. And it would be terrible to go home and realise one of the ones I didn't have. And the ones I do have, I'm always lending to people and they're never giving them back. So it's worth getting more of them. So he's just absolutely fantastic. He died, I think he was something like 95, but he was an awesome guy. And in honour of Martin Gardner, I'm going to put as many puzzles as I can in today's lecture. So let's go there. Oh, and the journey, not the end. Yeah, that's sort of what I wanted. That's, I guess, what I learned from Martin Gardner books is that learning, and in general life, I guess, is more about the journey than the destination. So you could always be deferring gratification, looking for some future payoff and some hypothetical date. But the fun things about reading his columns were the ideas that I had as I was moving towards a solution to the puzzles were just as interesting as the solution. So you could always flip to the back and look up the answers, but I soon developed a rule that I would never ever look up the answers because I wanted to go through the journey of working them out. So I hope you do the same too, that when you see puzzles that are playful, fun puzzles, that you don't spoil it by looking it up or Googling the answer. You work as hard as you can to find the answer. And just remember that it's the journey that's the important thing. That's where you learn the things. He had all the life skills you could imagine. He had skepticism. In fact, I think he was a founding member of, or certainly he's famous in skeptic circles and for debunking mathematicians, for magicians, sorry. Supporting mathematicians, debunking magicians. Supporting astronomers, debunking astrologers. Got to get it the right way around. He's a complete legend. So in today's lecture, I'm going to, at various times, talk about various things, and some of you will already know the destination. And can you please just not call it out? Because it's the journey we're going to take to the destination that's the point of today's lecture, not actually the answer. So calling out, oh, you could just do this by that, you know, that's not what we're... Okay. Okay, now, remembering versus working out is the next thing. You're coming up to your exam time, and I know when I had exams at school and uni, less at uni, I would never bother studying or learning anything because I have the world's worst memory, so it's not much point. It's like pouring water into a sieve. Instead, I'd just go into exam and I'd try and work everything out from first principles. And if I was lucky, the lecturer taught me first principles. And I felt confident that I could eventually work everything out. So as you can imagine, my exams were a few questions brilliantly answered. Most of the exam not answered at all. And I never really did very well at school. And I think it's because I always worked things out. I never remembered things, and that's not because of any particular virtue, though I now do think it's a virtue, but it's because I had a bad memory, so I had no choice. Now, I then started to tutor people for high school, for the HSC, and I learnt from my own mistakes. And what I'd always tell the students that I was tutoring, especially in maths, is I'd drill them on speed. I'd say, we're going to look at the fun thing, and we're going to see how it all works. And we're going to understand everything, and we're going to understand first principles. But then you are going to memorize various halfway points, because in the exam, you've only got 4.5 minutes to answer this question. And if you have to work it out, you're not going to get the question done. So you have to know straight away which method to use, where to start, what lines, and where the errors are likely to creep in. So our lessons would be structured in that way. A bit of fun and a bit of memorizing. A bit of fun and a bit of memorizing. So I think for time reasons, it's sometimes really important to remember things because working out can just take too long. I was looking at Gwen this morning. She every day used to go to school forgetting something or missing something. She'd go and she hadn't brushed her teeth or combed her hair or packed a sports uniform or put a library book in, or there was no hat in the bag, which means no play, no hat, no play, or there was no jumper, or the homework wasn't there. And just every morning I'd just say, come on Gwen, put it all in, and she'd just try and she'd forget something. So now what we do is we have a big chart by the door with pictures of everything, and you just go down the chart checking. Got it, 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 got it. Now this chart is like an external memory for her because she has, lucky her, inherited my excellent memory. But now she can get on the chart and check she's got everything. Now individually she's capable of doing all those things, but they just took a long time. The advantage of the chart here isn't that it's saving her time. What's the advantage of the chart in this case?
Don't need to remember stuff.
Because, yeah, what's the problem it's solving? That you might forget something important. It's not that you can work it out. You can't work out, I've got to bring my homework in today. Or, no, that's a bit arbitrary. You can't work out that it's ballet today, or maybe you could. But there are some things you just can't work out. You've just either got to know them or not. You've got to remember them or not. Maybe you can work everything out. No, I don't think you can. Some things depend on arbitrary facts, that if you don't remember those facts, you can't remember it. So sometimes it's really important not to forget everything. So I think writing things down you do for two reasons. One is it saves you a bit of time, and two is it stops you overlooking things that are really important if there's a serious consequence of overlooking something important. Now, this weekend that we just had, while you guys were working without pay on a really hard problem, I was off in a lighthouse. A friend of mine got us a gig in a lighthouse, and by gig I mean a bed. And so we slept in a lighthouse. It was fantastic. It's the best weekend I've ever had. And I was made better in the wind and the things howling around us and the sea smashing below. It made me feel really cozy. You know, when everything's grim outside and you're safe inside, it makes you feel extra warm and cozy. But I felt extra relaxed thinking of you guys. So it was just the best weekend I ever had. Now, something that I never ever can work out, and I always get wrong, sorry. I actually was thinking about you and worrying a little bit, and it was thank heavens that I had no possibility of going on the internet, or I'd have just completely fretted myself to death. I never can remember when someone says it's a sou'wester, does that mean the wind is coming from the, don't want you to call this out, does that mean the wind is coming from the southwest or going to the southwest? Now it could be either, both are equally plausible. You have to remember which one it is. You can't work it out. And I always get it wrong. And the problem is people have told me 50 times, so I now know it's one of them. But the problem is I can't work out which, because I can't work it out. There's two possible solutions to that puzzle. Neither seems more meritorious than the other, so I can't derive it from first principle. I'd only know it if I could remember it. Well, this weekend, I suddenly worked out how to remember it, because there was a weather vane on top of the lighthouse. No, on top of the dwelling next to the lighthouse. And it had one of those, it had like an arrow. Does that make sense? And a vane. But here's the interesting thing. At the back of the vane, and I realise now I've always noticed it, it's sort of splayed out. It's splayed out in the third dimension. I can't draw it, but sort of went out here, and I'll look at it from above. From above, it looked like this. And the arrow, you can't see it because it's now in that Yeah, but you get the idea. Look like that. And the fixing point goes, I'm looking down at the ground now. There, see, there's me, down below. And there's someone else. There's the cliff. There's the cliff, there's the sea. See, we're looking down. Okay, now, and then there was just a normal north, south, east, west thing set up. Frame with north, south, east, west attached to it. Oh, no. Does that make sense? Yeah. Now that's the sensible way of making a weather vane. I'll remember that because if I was going to make a weather vane, that's how I'd make it. I don't think there's two equally plausible ways of making it. I think this one clearly makes more sense to put the fat end here, not where the arrow is. I always think the fat tail goes the opposite end to the arrowhead. So now that tells me instantly, what does it mean when the wind blows? I can work it out because I can remember this because it makes sense. Now I know when the wind blows, which way is it pointing? If it's pointing this way, which way is the wind blowing now? The wind is blowing this way. Yep, because if it was facing the other way, if the wind was blowing this way, this would be unstable and it would flip round. Can you see that? Because the vane splays out like that. So anyway, I can just remember it. And then, within seconds of being excited that one of my biggest dilemmas in my life had been remembered forever, I realised that there's this line in The Hunting of the Snark by Lewis Carroll that also gives the answer away. And if I'd only remembered my Hunting of the Snark, I'd also know the answer. It's this little joke where the captain essentially says, the captain's completely hopeless, and he said, I'm sorry I keep getting lost, but you know, who would have thought that when the wind's blowing from, when it's a southeasterly wind, I'd be heading northwest. And yeah, so that's very funny. Because that's what you do. Okay, it all makes sense. All right, so two other things to try and remember. I can never remember which way to turn a screw. That's something else I can't work out from first principles. I look down at it or how to turn a tap to turn the tap on. Which way tightens it up, which one untightens it? My mum said something. She said, oh, it's easy to remember. I used to forget. Remember this rhyme. And I thought, oh, I'll remember a rhyme. Turn right, screw tight. And I said, what? Mum, that doesn't make any sense. Because if I'm turning right at one point, it's turning left at another point, it's going up at one point and going down at another point. You know, and it's going up, down, and side, you know, at all points it's heading in all directions. There's no turn right for a screw. That doesn't make sense. She says, it works for me. For years I couldn't remember it, and then one day I remembered when I was young how I'd unscrewed my dad's clock because I wanted to see how a clock worked because it completely amazed me that a clock could work. So I took off the main plate at the back, and there's an enormous thing in there called a main spring, which is held in place by screws, which I'd all carefully removed. And as soon as you loosen it a bit, it goes pa-lang! And all around the room were little gyroscopes and wheels and springs and cogs. And I carefully gathered them all up and poured them back into the case and screwed the back on the case. Now the clock shook and it made a rattling sound. But I thought, oh, I can remember because to undo something, it's anti-clockwise. It's to destroy a clock. So I could remember that. Yeah. And the last thing, and I still don't know this, and maybe someone can help me, is again at my mother's house, she's always trying to catch me out. There's this thing called a mixer tap. I don't know if you guys have seen a mixer tap. It's like a nozzle, there's a handle coming off the tap, and then there's like a blue pitcher over here, and there's like a red line over here, and this is a handle, and they think it's clear, and here's the sink. They think it's clear what you've got to do. And I go, well, I don't know. I guess the red is hot. I can work that out. But do I move the hot towards me? Is there is there a gauge back? Is a dial back here and I move the hot towards the dial? Or is in fact the handle a bit like a gauge and I rotate the red towards the thing here? Which way is it? Both seem equally plausible. Or is it, this is telling me which way to turn the handle relative. So maybe moving the handle that way is trying to move the handle towards the red. I know they're fixed together, it'll never get there. They all move together, but they're three plausible interpretations. They never make sense. So every time I do it, I burn myself. I can only do it through trial and error. Just push it one way, and every time someone tells me and I remember, and it's one of the three plausible ways, but that's all I can remember, that it's one of the three plausible ways. They all seem equally plausible to me. So I have to try it by trial and error, and like with Gwen, in that case, when I get it wrong, it causes me pain. And when I get a screw wrong, you really bugger it up. If something's tight, really tight, and you want to unscrew it, and you're turning it the wrong way, you're making it even worse if you're trying to unstick it. So, yeah. Okay, The last thing that I can't remember is how to convert miles to kilometres. And I always have to do this for various reasons. I don't know why, but it always comes up and someone says, oh, I know I'm reading an old book with the saint and he's travelling down the road at 60 miles an hour. And I think, I want to know what speed that is so I can relive the experience in my mind. But how can I convert from miles to kilometres? It seems I could bing it. I could bing it. I could bing it. Okay. Now, let's just look at this notion of recording things and remembering versus working out. What mankind does over and over again is we work things out. We're not very good at remembering things. So one thing we never seem to work out is that when you have a revolution, very soon afterwards, it's just as bad as it was before. There's just a new guy at the top. This happens over and over again. The French, when they had their revolution, they modeled their republic on the Greek notion, on the Roman notion of republic. But if they'd paid more attention to their Roman history, they'd have known pretty soon someone came to power and he was really powerful and he was a tyrant and he turned it into an empire and he was an emperor, and then the whole thing quickly stopped being a republic very quickly. But they forgot that and they appointed Napoleon to run them. And this happens over and over again. Every time someone has the Russian Revolution, there's a million revolutions. You throw the old guys out, everyone's really angry, you put someone new in, 3 weeks later they look the same as the old guy, then they're the tyrant again. Now, if you learned history, you'd see that was going to happen. But I think mankind's not so good at learning from history. We tend to make mistakes over and over. And in my security course, for example, we often talk about conflicts of interest and corruption. Because it turns out one of the biggest problems in a security setup is not the actual protocols or the hardware or anything like that. It's the wetware. It's the people in the system. The human element's what lets it down. And so I used to, when I taught security, I kept a scrapbook, and over the year I'd add interesting stories to the scrapbook that I cut out of the newspaper, showing essentially how someone in a position of power, so they had responsibility to, say, an organisation, but they also have a responsibility to themselves. This is called conflict of interest. Yeah, it always happens when you're in power. You have to look after your government and you have to look after yourself. You have to look after your church and you have to look after yourself. You have to look after your soccer team and you have to look after yourself. There's always a conflict of interest, and it's just managing it you've got to do. And corruption's when you don't manage it, when you start to actually think, well, actually, I might let the country, I'll do things that I'm not supposed to be doing for the country. I won't act in the country's best interest. I'll act in my own. I'll make myself richer and powerful and have fancy apartments and so on and so on and so on. And this always happens, that people, once they get in a position of power, they get conflicted. Of course, that's the nature of being in power. And then they eventually give into it. And corruption just happens over and over again. And so I wanted to show students how this happened in the security course, because it's very important for us, because we have people in positions of trust in any protocol. And you want to see that actually this is the weak point and this is where the system's going to fail. So I used to cut out articles from newspapers to show them, compelling examples from the real world of how people give into corruption. And I soon realised that my wife said, what's that enormous pile of newspapers there? Because every time I'd read the newspaper, I'd go, oh, there's 17 articles in here I want to cut out. Oh, I don't have time to do it now, I'd stack it up. And every paper I touched had, little post-it notes all over it and things, and I just kept in a big pile, and it got ridiculously big. And Kate said, when are you going to put it in a scrapbook? And I suddenly realised I don't need to put it in a scrapbook. And I threw it all out, because I can pick up a newspaper on the way into a lecture and find 50 million examples of people giving into corruption. And why does it happen? Largely because we know all about this, but we don't learn from it. We set systems up. We don't learn from mistakes. We don't record what's happened. We don't look at history. And lo and behold, we have the same mistakes happening over and over again. So let's look at the question now. When is it worth to write something down? When would you want to write something down? Because it's a pain to write something down. When should you do it?
When you're doing a wiki commentary for the week.
The wiki commentary is a great example. Why is it worth writing it down?
Because while you can remember the gist of the lecture, if you're going to do the details,
yes,
you really need something to refer to.
Yes. What's the advantage of us doing the wiki? What's the advantage of some people writing it down?
Everyone else can see it too.
Everyone else can see it too. So we do a small amount of remembering, and it saves a whole lot of work. It saves everyone having to write it down. So that's fantastic. So that writing it down is a work-saving reason. So that's a reason, I think, to write things down when they would otherwise have to be done multiple times. In this case, it'd be done multiple times by multiple people, but perhaps it'd have to be done multiple times by you. Like every time I set up a machine now, I've got a how-to that I keep on my own wiki of how to set up that sort of machine. Because otherwise, I can't remember how I set it up last time, except vaguely, and I have to go through all those painful mistakes of getting the wrong device drivers and things in the wrong order, and I have to do it over and over again. And once I write down the how-to, it's so mindless. I just go through the steps. Oh, do this, do this, do this, do this, do this, do this. And if I get a slightly different configuration, slightly different, I just have to change my notes very slightly. So that saves me time. So I reckon it's worth writing things down when you do them multiple times, or when multiple people all do them once, because that saves time. And the other reason for writing things down is practice. Yeah, actually I hadn't thought of that. The actual act of writing something down can force you to express it, and the act of expressing it forces you to think over it and perhaps transform it and interact with it in some way, and actually that can help you understand it. Yeah. Absolutely. I used to do that for Indonesian. I used to try, I was shameful when I was a teenager. I used to try and cheat in my Indonesian exams because I paid no attention to Indonesian except for the 3 days before the exam. And I used to cheat. And here's how I'd cheat. I'd say, oh, I don't know any of these words, so I'd look at the whole vocab list and I'd write it on a scrap of paper. And I'd try and get it small enough I could fit in my pocket. So I'd just write it out and out and out, and every time it wouldn't be small, so I'd write it a bit smaller and a bit smaller. And the good thing was, as I wrote it out each time, I'd remembered a few more things. So not only was I writing it a bit smaller each time, I was remembering more each time, so I had less to write. And eventually I got it on quite a small piece of paper. And then I thought, oh, I'll just keep iterating this process. And then eventually I got it onto a ridiculously small piece of paper. And then eventually I didn't even have to do it. Yeah. So yeah, absolutely. The act of writing something out has value in and of itself. I'd forgotten that, for humans at least. I think the other thing is importance. That it's worth doing it to save repetition, which saves you time. And it's worth doing if the thing is so important that forgetting to do it will be a catastrophe. So then we write it to make sure we're complete and consistent. Now, when we did the example before of Phineas Fogg in the room with all the doors, and he tried all the keys in all the doors. Remember, there was a key for every door, and he had 300 keys and 100 doors and 3 locks in every door, and he went around trying them. One clever thing that someone suggested was, to speed it up for him, every time he worked out what key went in what lock, we should leave the key in the lock. In a sense, that's remembering you've used that key. And if you know you only have to use a key once, remembering you've used that key is a really important information because it'll save you time. So we can see there that remembering saves us time, but I should point out, does it actually change the complexity of that problem? If there's n doors and you didn't save the keys, how much work do you have to do? 3 keys to try for each door. Yeah, how much work do you have to do? Essentially, you've got to try, work it out. You've got 300, say you've got 3n keys for every lock.
I think we said it was billions or something.
Yeah. You 3n for the first one, and then you have to try 3n for the next one, and you have to try 3n for the one after that. So that's 3n plus 3n plus 3n, that's 9n work per door. And if you don't remember which key you've got, is 9n times the number of doors, which is n, 9n squared, so it's quadratic work. Now, if when you find it and it fits in the lock, you don't have to touch it again, then you have to do 3n work for the first one, but 3n minus 1 work for the next, and 3n minus 2 work for the next, and 3n minus 3 work for the next, and 3n minus 4. But if we work all that out, what's it still going to be? What's the sum of all those numbers? It's still going to be order n squared, isn't it? Let's not worry about the precise details because it's going down and down and down. But remember, that's that one formula I told you once upon a time. I said, if there's one formula you have to learn in computing, it's the sum of all the numbers is roughly n squared on 2. It's order n squared. So there, it's saving us time, but it's not changing the complexity of the problem. So sometimes we'll consider that a reasonable thing to do, and sometimes we'll think it's not worth the bother because really we're after a bigger change than that. We're after a complexity change. Okay. Whew. Miles conversion. Here's how I do a miles conversion, by the way. I learned how to do it from reading a Martin Gardner book. Martin Gardner is the most awesome man in the whole universe. And in reading one of his puzzle books, and they're not really puzzle books, I'm not actually giving the right sense saying that. They're books just about mathematical ideas. Every chapter just follows some fun mathematical idea and looks at interesting angles on it. And one of his chapters was on the golden ratio. It's very, very beautiful. It turns out the golden ratio pops up all the time. Also, inaccurately, people think it pops up in other places where it doesn't. Like, everyone's always talking how it turns up in early architecture, and now there's a lot of skepticism about whether it really does that or whether the people measuring just adjusted their measurements to make it turn up. Nonetheless, the golden ratio turns up all the time. The golden ratio is approximately 1.61. Why is the golden ratio really important? Well, there's one little cool fact that I remember about the golden ratio, or two cool facts I remember about the golden ratio. One is it's approximately equal to the ratio between the length of a mile and the length of a kilometre. Oh, in nature, it's popped up again. It's only approximately, but that's good enough for me. And the other thing that I remember is successive terms in the Fibonacci sequence approximate the golden ratio. Fibonacci sequence goes, you guys tell me. 1, 1, well, we should have started with 0. 2, 3, 5, 8, 13. Is there anyone here who does not know how we're generating the sequence?
From memory.
We're not doing We only have to remember two things. It's so beautiful. This is what I love about maths. You only have to remember the axioms and the whole system emerges from them. So, and that's not a hard thing to remember, 0, 1, is it? Yeah, we add together the previous two numbers to get the next one. So here 13 was 8 plus 5. And we just recursively keep doing that. So the next one would be 21. Now, it turns out the ratio of successive terms approximates the golden ratio, and it's actually converging on the golden ratio. So 1 divided by 1, that's 1.0. That's not a very good approximation of 1.6. The next one's 2 on 1, that's 2.0. That's not a good approximation either, but it's getting a bit closer. And the next one's 1.5. And the next one's, what am I doing? Here gives us that, here gives us that, here gives us that. Let me just get it lined up. What's 5 on 3? 1.66. It's going to get closer and closer and closer. So here's how I convert between miles and kilometres. If it's any number in the Fibonacci sequence, then I just have to pick the next number in the sequence or the previous one. And that gives it to me. So if it's 80 miles an hour, 80 miles an hour is approximately 130 kilometres an hour. 80 kilometres an hour is approximately 50 miles an hour. The further on you get, the better the approximation is, but it's damn good. So now I can convert between the two without having to remember anything at all. You can just do it from first principles. Martin Gardner told me that, bless his soul. He lived to 95. Can you imagine that? He deserved that. And those 95 years were so well lived that the product of length times quality is such an amazingly big number. It's probably the biggest it's ever been had in the human race, I reckon. He's an awesome guy. So now I want to show you some sample code because, of course, the only problem here is calculating those damn Fibonacci numbers. So I've written a program to do that. Let's have a look. Yeah, here we are. Oh. Now, actually, first of all, do you remember last week, John presented the decorator pattern, and he presented it really well, and at the end I was so excited, what a clear definition he'd given it. And then I looked through the wiki notes, and someone taking the wiki notes said, decorator pattern, question mark, question mark, question mark. And that was their entire notes for the decorator pattern. I thought, whoa, I didn't get it. And he explained it so well. Oh, okay, how can I explain it in a different way to help those people get it? And then Mike, while I was just cogitating happily on the decorator pattern immediately after John's lecture, sat up and he spoke, do you remember about the symmetries of the square? And he used a Beatles album and he rotated it and talked about transformations on a square, mapping it back to a square. And he talked about an algebra of transformations and how that was a simple group and so on and so on. And I thought, okay, that's how I'm going to demonstrate it. So I wrote a decorator pattern to do the symmetries of a square. He did it on one album, but I've done it on Hard Day's Night for reasons hopefully that are apparent. The Hard Day's Night has a picture of all 4 Beatles in a square. So as you rotate now, we can label each album by the pictures of the Beatles. The biggest problem I had was working out which Beatle was which, because they all look the same to me. I'm not enough of a Beatles fan to work it out. So I got all these photos from the same time, and I was on the phone to Roland, my PhD student, and I was going, do you think that one's George? And we've all got hundreds of pictures of George, and he's saying, look at the eyebrow, there's a little dink in the eyebrow there. And George at that time has a dink in the eyebrow. I said, yeah, but look at the haircut. It's, you know, they're all identical people. So the symmetries of a square aren't that interesting if all squares are the same as all other squares. So here's what we've done. So here's a bit of code. I'll put it up for you. But you can see it found 8. Mike said as a challenge to you, how many different symmetries are there? How many different ways are there? One of them is to get a Hard Day's Night and you rotate it and you rotate it again. One of them is to just rotate it. One of them is just to have it and not do anything to it, the identity transformation. One is to reflect it. One is to rotate it first and then reflect it. Oh, reflect it first and then rotate it. One is to rotate it, and rotate it. And the other one is to rotate it and then reflect it. And the last one is to rotate it, and then reflect it. And that gives you all 8. And I did that using decorators. So I'll put all that code up, and I might even put up a little blurby with me chatting about it at the same time. So go and check all that out. But now let's look at Fibonacci. Here's our Fibonacci. I've written a file a class to represent Fibonacci numbers. We're going to want to do something funny and fiddly with our Fibonacci numbers, so I want each one to actually be an object. We could just have it as an integer, couldn't we, and have a function that computes it, but I want each Fibonacci number to be an object. So the object's going to store n, which is which Fibonacci number it is. So the third Fibonacci number here would store a 3 here, for example. I'm Fibonacci 3. And then when you create it, it just checks you're not trying to make a negative one, though it turns out you can, but let's for the moment say you can't. And just stores the value you created it, so that if you want to make new Fibonacci 3, it'll make a new Fibonacci 3. And then we've got this function here to compute called getValue. So given a term in the Fibonacci sequence, you can say, what's your value? You can go new Fibonacci 3, and then you can go, that object I just made, getValue, and it'll tell you the third Fibonacci number. I keep saying third, it's actually the fourth because we're starting from 0. And here's how it does it. If n's less than 2, then the value is just the number. So the 0th one is 0, the first one is 1. If it's 2 or more though, it uses this. It calculates the Fibonacci number before, which is Fibonacci n minus 1. The Fibonacci before that, which is n minus 2, gets the value of both of those and adds them together, and that's its value when it returns that. Does that make sense? And I've got a Fibonacci user here that actually does it. So let's have a look. Let's say, what's Fibonacci of 1? I didn't put any IO in. We have to recompile each time. I know it's pathetic. Okay. Fibonacci of 1, and it says, oh, let's run you, run. Fibonacci user, run. Do. Fibonacci calculator. Ba, ba, ba. Fibonacci of 1 is 1, and it took 0.0 seconds. That is always very nice, isn't it? It's the 0.0 that impresses me. Now, what if we wanted to find the fifth Fibonacci number? The fifth Fibonacci number is 5. Ooh. This doesn't look like a very sophisticated program. What's the sixth one? Is that right on our list over there? Sixth one should be 8, should it? Yeah, Fibonacci 6 is 8. What's the 26th one? Oh, they get big pretty quickly. And you know they get big pretty quickly because I told you the ratio between successive terms is converging towards 1.6. What does that tell you? They're an exponential growth with a multiplication factor of 1.6 each time. It's going to grow exponentially. So 26 is getting quite big. What about 36? Woohoo! So if someone said, oh my God, that meteor is traveling at 14,930,352 kilometers an hour, how fast is that in miles? You would simply say, oh, that's easy to calculate. It's just the same as 9,227. And they go, oh, that is scary, man. Yep, does that make sense? So there's our Fibonacci thing. Now, look at the problem. Well, I guess you don't know what the question is. What's the question? The question is to be or not to be. Yeah. What's the answer?
Yes.
To be or not to be? And the answer is no. It's 2A. Or 42. So we're going to try it with 42. Here's our Fibonacci oh, it's broken. What? That 0.0 seconds is taking longer than I thought. What? It took 10.1 seconds? What? How did that happen? It was going up to 38 or 39, it was 0.0. Why is it taking 10.1 seconds? You could calculate the 40th second Fibonacci number in less than 10.1 seconds, couldn't you? No. No? Well, maybe you couldn't. But could you calculate the 43rd one? Because the 42nd one took 10.1 seconds. What's the 43rd one going to take? Is it actually running? What? 16.2? 16.2 seconds? What? How long's 44 going to take? Well done. I wonder if there's any sort of ratio between these times. Which is, who said it? You said it. You said it. You said it. You said it. Hold on. How long did it take? Is it running?
Not done yet. Yeah, it's still going. Yeah, it's still going.
How long is it going to take, do you think? 40 seconds? 1.6 times 16? Well, I'll do the 1 time and you can do the 0.6 times. Oh, 26.6 seconds. Whoa, why is it taking so damn long? It's just multiplying. I'm not asking it to count to the Fibonacci number or anything like that. It's just adding things together. What's going on? Well, let's look at our program and we'll see what's going on. How does our program work? To calculate the Fibonacci of 43rd Fibonacci value, it creates it. First of all, we go new it, and it makes it. Saves 43 inside n. And then when I say get value on it, what does it do? Oh, it makes a Fibonacci object for n minus 1. So it makes a Fibonacci object for 40, 1. And it makes a Fibonacci object for 40. Then it calculates their value and adds them together. All right, now how does it make the Fibonacci? Well, let's have a look at what it did here when it creates this guy here. It just stores 41 inside it, the new object. Now what happens when I go get value on that new object? Oh, well, hang on. Oh, what's going on here? When I make the 42 object and call get value on it, it creates a 41 object and it also creates a 40 object. It makes new objects. When I ask the 41 object what its value is, what does it create? It creates a 40 and a 39. What? It did that twice, the dumb thing. What does 40 do? Well, it makes a 39 and a 38. Hang on. Whoa, and what does this 40 do? Well, it makes a 39 and a 38. Whoa. So, we're making multiple repeated objects here. This is not very good. If we went to Fibonacci user, and we didn't want to do the long one, perhaps we just did the one that takes Fibonacci 41, which I don't think we know yet how long that takes to compute. It should be very quick, shouldn't it? 41, 6.6 seconds. What if we did this? What if I said, print the Fibonacci, the 40th one, and then I said, what? Say that again. How long is it going to take now? It's found the first one. Well, it took 12.6. Like roughly twice as long. What's going on there? It did it once, and then I asked it to do exactly the same thing, and what did it do? It worked it out again. It's an idiot. It's like me doing an exam. What it should do is remember, shouldn't it? It should remember. I've already worked that out. I told you once. It should just be able to tell me. So let's change it round so it can remember. And we just change our Fibonacci class. How do we do that? Well, you know, one thing we could do is this. We could store the value. And we could call it value. And then when we create the damn thing, we could do the calculation when we create it. So it only happens once. So now it calculates the value on creation. That's only going to happen once. And then to get value, that's easy. All you return is this dot value. And we don't need you anymore. Now let's run it. Fibonacci calculator. It takes a long time to create the object to start with, but the second call takes no time at all, and the whole thing takes 8.5. Yeah, we moved a bit more work to the creator. It turns out it's a bit more inefficient to do the stuff there, the way things are set up. So it didn't take 6.6, it took 8.5. But the point is it just did it once. Does that make sense? We call that memoization. Memoization is we remember something we've done once. So if we have a task we do multiple times, then let's only do it once and remember it. Does that make sense? Okay. However, there's a downside to doing it this way. In the past, I could have created 50 Fibonacci numbers and no work was actually done till I said, get your value. The problem was, if I said get your value twice, you worked it out twice. But maybe sometimes I don't ask you to get your value. I can make Fibonacci of 1,000,000, not get its value, and it would be done in 1 second. And I could only call its value if I really needed its value, so I could preemptively calculate it. The way we've done it now is the Fibonacci value is calculated as soon as we create the object, regardless of whether we even ever use it or not. So we don't want that. So what we really want isn't this. We really want something that only does the calculation when we request it to do the calculation. But if we request it to do the calculation twice, we want it to remember the previous value. We only want it to do it once. And that's easy to do. We just change our code round. Actually, we change it round so it looks a bit like it was before. We just say, oh, we're not going to create it on construction. Instead, we're going to create it when they go get value. And we're going to say, what are we going to say? Something like, if this dot initialized, if it's initialized, then we'll say, no, if it's not initialized, sorry. If it's not initialized, we'll initialize it. And then we'll return the value. And we'd better say, once we've initialized it, start. So if it's not initialized, we'll initialize it. So when we call it, the very first time we call it, oh, there'll be a problem with initialize because I haven't declared it yet. So we create it, it's not initialized. The first time you initialize it, it gets initialized, and then on it just returns a value. Whew, let's run it now. Oh, and it did it all for us, and it took 8.4 seconds. So it, there's a lot of extra ifs going on in there, isn't there? So it's a bit more overhead, doesn't take the 6.6 again, but it's saying, now if we don't call it at all, oh, I better check it when we don't call it at all. Now if we don't call it at all, it'll be super fast. Let's do nothing. We'll create the object, new Fibonacci n, but we won't actually do anything with, we won't ever query its value, and then now that should happen lightning fast. There we are, 0.0 seconds. So here's our idea. Our idea is this. When we call a function on the object to set up the object's value, we only set it up once, and we don't bother setting it up until it's needed. We don't set it up when we create the object. This is a great idea that's crept into lots of programming languages. It's called lazy evaluation. So you can create things and have expressions, and you can say to the computer, work this out, and it goes, yeah, sure, I'll work it out. And it puts it in a big pile of newspapers by the door. And it doesn't work it out until you ask it what the answer is. And if you never ask it what the answer is, it never bothers to work it out. And languages that are lazy are awesomely clever. You can write programs that very, very simply, without having to optimize anything, and it's the actual flow of execution that does the optimization, where things are only calculated precisely when they're needed. You don't have to try and anticipate when they'll be needed and when they won't. Java, unfortunately, isn't a lazy language, but we've sort of made it lazy in this way. Okay, is everyone cool with that so far? But we're still taking way too long. We can ask it the same answer twice, and now it'll take as long as it took the first answer. But it wouldn't take you. Let's think, if it's exponential, and 44 took 26 seconds, how long is 45 going to take? I don't know, a minute or something, nearly. So 46 is going to take like a minute and a half. And 47 is going to take like, I don't know, 3 minutes. 48 is going to take like 5 minutes. And 49 is going to take, I don't know, 8 minutes. And I'm doing Fibonacci sequence now. And 50 is going to take 13 minutes. All right, 50 is going to take 13 minutes. I reckon now you could beat it. Do you reckon you could multiply 50 numbers together in under 15 minutes? If I gave you a calculator? Add 15. It's even easier. You could just write them down and add them up. Could you do it with a calculator? Yeah. Okay. Certainly would take you less than 15 minutes. So it can't be that a calculator is faster than a computer, calculator driven by your finger. It's got to be that we're doing something dumb. So what is it that we're doing dumb? Yes?
Recalculating all that state number.
Yes, that's right. We've still got the problem that every time we calculate 42, it creates a 41 and a 40 object. And the 40 object creates a 40 and a 39 and so on. So you've got, how many 42 objects have you got? How many 42 objects have you got in the, 41 objects have you got in the system? How many 42 objects have you got, 40 objects have you got in the system? How many 39 objects have you got in the system? Can you guess how many 38 objects you got in the system? 5. Okay, we've got exponential growth in the number of objects in the system. So this is what's killing us. Sure, we're saving a little bit of time around the edges, but we've got to generate an exponential number of objects, so we're doing an exponential number of work. So we've got an exponential algorithm, and that's crazy. So what we need to do is use our memory again. We need to remember stuff. By the way, let's find out how many objects we made, just for fun. I did put some code in to do that somewhere. Let's have a look. In my Fibonacci class, down the bottom, I created a private static variable. Do you remember static variables? I don't know if I've ever explained a static variable to you. It belongs to the class, not the object, so it's shared amongst all objects in the class. We've made static constants. It's very rare that you'd make a static variable. It's normally used as a sort of global variable. It's normally a bad thing. But in this case, it's a sensible thing. We've got something called count, which we set to 0, and a function called getCount, which returns the current value of count. And every time we run the new function, let's increment count. What's it called? Fibonacci dot count plus plus. So every time you run a new, it updates a count. So the class itself is keeping track of a counter that records how many objects are created. And let's at the end print out the number of objects that were created. Println, where do we go? I commented out the actual work. We should probably stick that back in for one of them and say I created this many, I created percent comma D objects.
Why the comma?
Comma means I like the commas between groups of 1,000, if that makes sense. I like it formatted so I can understand what's going on. I mean, no, I want to printf, don't I? Now, printf is hopeless, never sticks a print line, never does a new line on the end. So let's stick one in manually. And did I do Fibonacci? Oh, thank you. Fibonacci dot, what did I call that field? Get count. Oh yeah, that's right. That would be bad if I access the field. I should always access it with a getter. Okay, we're done. Oh, there it is down here. I've done it below. Oh, well, it doesn't matter. We're running it now. Fibonacci calculator. It's running it for 40, can't remember what it was. It'll tell us. Was it 42? 41? 40? 41. I created 500 million objects. Woohoo! That's fantastic. Good on it. Good on it. Now, we've asked it to do a lot of work. But if I was to ask you to calculate the 40th Fibonacci number, would you do 500 million calculations? Would you make 500 million notes on bits of paper?
Yes.
Okay. So the problem is we're creating these objects over and over again. What we'd really like is the first time you create Fibonacci 40, we'd like you to create Fibonacci 40. But the next time you create Fibonacci 40, what should you do? Just return the other one. Because if everyone that's got a Fibonacci 40 has the same Fibonacci 40, then as soon as any one does a get value, all are now pointing to an object where the value's been calculated. You don't have to calculate that object over and over again on each object. Because you don't have to calculate that. You don't have to do get value. You don't have to do that calculation on every single object because you're all sharing a common object. So you do it once, woohoo, everyone gets it. Okay, so let's do that. How do we do that? Oh, can I leave that as an exercise for you guys? How would you do it? Tell me. If I wanted to do it so that when you made a new one of them, if it already existed, it wouldn't make a new one. It would give you a pointer to the one that already existed. How could you possibly do that? With a factory. Why do we need a factory?
Because then when you call the function to create it,
yes,
it can do something that says
yes,
it already exists.
So we need a factory method, or a creation method at least. A creation method that does this. We have to hide the constructor. Because if we leave the constructor floating around, then people are going to construct lots of these objects and it's going to spoil it for us. So we hide the constructor by making it private, and we add a creation method to our class. And the creation method, what does it do?
It checks if it's been created.
How does it know if it checks if it's been created? If it hasn't been created, it does a new, which it can do, even though it's private, because it's in the same class. And if it has been created already, it returns a pointer to the object that's already been created. So we need to keep track of which objects have been created. We need to have a pointer to them all. So we could probably do that with an array. Yeah, we could have that's one way of doing it. We could have an array of previously created objects. And then when someone wants to make a new one, we'll check if that object's in the array. And if it's in the array, we'll just give them the reference to the guy in the array. Does that make sense? Where would you store this array? Statically. It has to be statically. It can't belong to an object because you haven't made an object at that time. So you'd stick it in probably inside Fibonacci, the Fibonacci class. You'd have a static array that kept a reference to all the objects that have been created. And you'd have a static creation method. And when you call a static creation method, it would check the array and return that guy or return. Now you guys can write the code to do that. Okay, that can be your exercise. Because I want to take a little break because I have some more exciting stuff to show you after the break. Now before we have the break though, blah, 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 blah. Puzzles. I need to tell you the hats puzzle. I need to talk about hats because people aren't wearing enough hats. We need to talk more about that. And I also need to I need to show you Dan's cannon, and I need to give you the barometer. I also need to mention something. What we just talked about then, this idea of only making one of the thing, and if anyone else tries to create it, you give them that thing back. That's actually a design pattern. We do that over and over again in OO programming. It's a really familiar thing. Someone even called it out before. That pattern is called the singleton pattern. When you want to have it so when someone creates an object, you only get one of that sort of object made, and anyone else tries to make one, they get a reference to that one. That's called the singleton pattern. And in the Fibonacci sequence calculation, once you implement it and see how fast it is now, you'll be amazed at the power of the singleton pattern. Does that make sense? So does everyone think they understand the singleton pattern? Did you get the idea? Creation method, don't give them access to the constructor function, check, again, keep somehow a list of the things you've already made, give them back one of those lists if it's already made. Yep, homework for you is to try and implement the singleton pattern for the Fibonacci class. Does yours have a VGA output? Could you look up for me? Oh, no, in a second. We'll do it in a second. You got sound? You got sound? You don't have a sound. Can you do it? Do you have sound and internet? Okay, I'll tell you what to look up in a second. Hats. We need to talk about hats. Edward de Bono talks about hats as a problem-solving technique. Has everyone read about Edward de Bono's ideas about hats? I think everyone should wear lots of hats to the exam. You have. Jackson, you've read it.
Software engineering, yeah.
You do it in software engineering. Tell us what you learn in software engineering.
There are multiple hats, and you use each hat for like a different style of thinking. There's one where you want to solve, and then there's one where you want to work together.
Yes. The idea is instead of just approaching solving problems as a big mush and saying, I just do the problem-solving thing now, he identifies 6 different ways of solving problems, 6 different behaviors or activities that can be useful. And he gives each of them a hat. And he suggests when you're trying to solve a problem, you go through in turn putting the different hats on, trying the different things. And one of the hats is come up with crazy ideas and don't be critical. And another hat is be really critical of ideas. Now, you don't want to wear that be critical hat at the same time as you're wearing the come up with new ideas hat, because as soon as you think of a new idea, it's very easy to poo-poo it. I could do this, oh, that'll never work. Yeah. You've all got friends and probably family that tell you that whenever you have a new idea, that'll never work. Okay? They said that about my plan to jump across the Grand Canyon on a box racer cart. Oh, that'll never happen. They were wearing the critical hat. I was wearing the plaster hat. So when you come up with crazy ideas, you want to come up with lots and lots of them, because at first it's easy to poo-poo the ideas because they're just little babies and they haven't got any form of substance. But if you nurture them, you could get surprising and amazing things to come out of these ideas. So the idea is you go through a brainstorming phase where no one's allowed to be critical about anything, and then later on you put on the critical hat and you winnow out the bad ideas. And you'll be surprised at the good things you get. So hats is really cool. I love hats. I love Edward de Bono. So I want to tell you about the hat puzzle. Some of you will know the answer to the hat puzzle. It's a lovely puzzle. I should say all these puzzles I do have solutions for, but they're all ones of my own because I hate looking up solutions. So quite possibly there are better solutions than my solutions around, in which case please don't tell me what they are, but by all means taunt me and say I know a better one than that, because that will excite me and make me look for another one, but don't tell me what it is. The hat puzzle goes like this. You're standing at the back, as often happens, of a very long line of people all wearing hats. And they're all either wearing, what's the make fun of people hat? The critical of ideas hat? What colour is that? What, it's got a spinning, it's like a propeller hat. Now that's the coming up with crazy ideas hat. All right, they've all got either the propeller coming up with crazy idea hat, or they're making fun of, that's the crown, okay? So they've all got a propeller or a crown on them. Everyone in the room has a propeller or a crown. It's a very heavy propeller, so just from using your head sensor things, you can't tell what you're wearing without looking at it. And you all had your arms sawn off, so you can't touch it. So, and you can't, it's glued to your head. There's no way of actually finding out what's on your head. But you're standing in a long line, no one's allowed to look behind them because you'll turn into a pillar of salt. It's a very constrained problem, but this happened to me the other day and I was glad I knew the answer to the... So you can only see everyone in front of you, but you can't see anyone behind you. Now, as a group, the evil princess is going to give you $1 every time someone calls out correctly what's on their hat. And everyone get what sort of hat they've got on. And everyone gets to call out just once, starting with the person at the back. So the person at the back can go, propeller hat. And the person in front of them can go, crown, propeller hat, crown, 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 propeller hat. And if we just did it randomly like that, on average, and you had, say, 100 people, how many gold coins would you expect to get? 50. Can you think of a strategy that will give you more than that? And can you think of a strategy that everyone in the room could follow that will give you the most coins you can possibly get? And can you prove your strategy is optimal? All right, so that's a fun puzzle, and we'll talk about that later on. Now, I said I never give answers to puzzles, but I do want to give the answer to the barometer puzzle. Do you remember the barometer puzzle? I will do that during the break. So if you don't want to hear the answer to the barometer puzzle, please leave during the break and come back when we've done the answer to the barometer puzzle. And now finally, Dylan, can I borrow your computer? During the break, I just want to play you a piece of a film.